Now this is an awesome fact, if you ask me. The velocity spins around, getting faster and slower at various angles, but evidently the laws of physics cook things up just right so that these trace out a perfect circle. And the astute among you might have a little internal light bulb starting to turn on at the sight of this circle with an off-center point. But again, we have to ask, why on earth should this be true? Feynman describes being unable to easily follow Newton at this point, so instead he comes up with his own elegant line of reasoning to explain where this circle comes from. He starts by looking at the orbit, whose shape we don't know, and slicing it into little pieces which all cover the same angle with respect to the sun. Alright, now think about the amount of time that it takes for the orbiting object to traverse one of these equal angle slices, and how that time changes as you go to a bigger slice. Well, by Kepler's second law, that time is proportional to the area of the slice, right? And because these slices have the same angle, as you get farther away from the sun, not only does the radius increase, but the component of arc length perpendicular to that radial line goes up in proportion to the radius. So, the area of one of these slices, and hence the time that it takes the object to traverse it, is proportional to the distance away from the sun squared. In principle, by the way, we're only going to be considering very small slices, so there won't be any ambiguity in what I mean by the radius, and the little arc length will basically be a little straight line. Alright, now think about how the inverse square law comes into play. At any given point, the force that the sun imparts on the object is proportional to 1 divided by the radius squared. But what does that really mean? What force is the mass of an object times its acceleration, the amount that its velocity changes per unit time. This is enough to give us a super useful bit of information about how the velocity of the orbiting object changes as it goes from the start of one slice to the start of the next. That change in velocity is the acceleration times the change in time, right? What that means is that this change to the velocity is proportional to the change in time divided by the radius squared. But since the time that it takes to traverse one slice is proportional to the radius squared, these terms cancel out. So the change in velocity as it traverses a given slice is actually some constant that doesn't depend on the slice at all. Here, unpacking what I mean by that, if you look at the velocity at the start of a slice, and then you look at the velocity at the end of that slice, and directly compare those two vectors by joining their tails, and you look at the difference between them, the little vector joining their tips. This difference has the same length no matter which slice of the orbit you were looking at. So, as you compare these velocity vectors at the start of each slice, they'll be forming some kind of polygon whose side lengths are all the same. Also, since the force vector is always pointing towards the sun, as you go from the start of one slice to the next, that force vector, and hence the acceleration vector, is turning by a constant angle. In geometry lingo, what this implies is that all the external angles of our polygon are going to be equal to each other. I know that this is a little tricky, but hang in there. Remember, all you need to follow along is infinite intelligence.